recording. That'll be important. Oh, logs. So like we were saying, Tuesday there's no classes because it's Remembrance Day. And then on Thursday, I can't make it. So that's a problem. So there's no lecture. But at first I thought I would kind of compile some smaller videos, but what I'll do instead is I'll sit down and record a video because I think it'll just serve us better in the long run. And so for section 4.6, which is everyone's favorite thing, word problems. So I know. So what I would, and I've got a note at the end, but I'll just bring it up now while I'm thinking about it. So there are the notes for section 4.6. And what they'll do is they'll introduce a concept like half-life, which you might have heard of already in your other courses, and then a word problem. Find the half-life. Given the half-life, find the annual decay rate, all these things. So there are no more concepts being introduced. I guess concepts in the way of what is half-life, what is doubling time, what is Newton's law of cooling, okay? And then I'll go through these and then orders of magnitude. And these are all kind of the typical word problems that we solve in this section, okay? And so what I encourage you to do is try these problems on your own, right? And then I'll go through them in the video. So if there's some that you kind of look at my notes and you say, hey, I got that, I did the exact same thing, then you can kind of skip that part of the video. Okay? And so it might be nice to try it on your own and see kind of how you think about a problem, and then you'll have the video where I go through it together. Okay? Nice. Any questions about that? So that'll be instead of class on Thursday next week. So I won't see you for a while. I guess until the 18th, I think. Yeah. Okay. So, any questions? Good. I have this little kind of summary down below, but I want to bring it up because I think it's the perfect review. I think it's just perfect. Look at this. So, we were working with exponential equations. We introduced logs last day. So logs are how we solve exponential equations. And so what we need to do is we need to first isolate the exponential expressions, if possible, which it will be. Then we take the log of both sides, and we talked about, okay, well, it doesn't actually matter which log base we use. Your calculator definitely has a log base 10 button and a log base E button. Okay? And my default is log base E, but there are times where I use a different base if it's more convenient. Why do we take the log of both sides? Because the log of b to the x can be rewritten as x times the log of b. And so it's this move of taking the log of an exponent that brings the x downstairs. So now I can solve for it. And so that's the key. And so, and I guess I should put this down here because that's the exponent property that it's talking about. So utilize the exponent property for logs to pull the variable out of the exponent, right? So if we wrap it up in a log, then we get the x outside. And then use algebra to solve for the variable x, which in this case is x. The main part is that you want to isolate the exponential expression. So just the b to the x part, or something like that. And I've got use for review on Thursday, and then we're gonna add some pages here. Well, here we are on Thursday, and we're ready to do it. I will need more room though. If I want to solve 6e to the 3x plus 1 equals 9, first thing I need to do is isolate the exponential expression. The exponential expression in this case, I'll do it underlined in green, is this part, the base and the power. And so step 1 is to isolate that. And so if we start at 6e to the 3x plus 1 is equal to 9, oops, 6 looks weird. What do I need to do? I need to divide both sides by 6 first, so I can isolate e to the 3x plus 1 is 9 over 6. Oh, brain's not firing on all cylinders, but we'll go with 1.5 for simplicity. You can leave it as 9 over 6 if you want. But I usually check to see if it makes something nice and then use that instead, if I can. So now, step 2, take the logarithm of both sides. Now, like we said last day, it doesn't matter which log you use, okay? But a sneaky trick is to use the same base as what you have in your exponent. Okay? So if you want, you can use the natural log, log base e, the ln. So then step 2, take the log of both sides. Here. So if I take the log of e to the 3x plus 1, oops, is equal to the log of 1.5, the log of a number is just a number. Right? And so you can kind of put blinders on and say, hey, that's just a number. It's a weird looking number. Yeah. But why did we do it? We took the log of e to the 3x plus 1 because I can. You guys didn't do it. You're paying too much attention to me, I guess. So utilize the exponent property, right? That's what lets us bring everything that's upstairs downstairs, if that makes sense. So now use the exponent property, which says that this can be brought downstairs and I get 3x plus 1, making sure you treat that as one thing. So I like to wrap it up in brackets. Yeah. Times the natural log of e is the natural log of 1.5. I already confessed the other day, or on Tuesday, I guess, that when I use the natural log, I tend to just call it the log, which I know can be confusing, but it is just a log base e. So I'm trying not to do that, but it's hard. Okay. And so here, right, make sure to treat this as one thing. So now what do we have? Well, we use the natural log base e because I have base e in my exponent, which tells me that this must be 1. Okay. Why? Do you remember? Recall that the log base e of e is equal to, so e to the power of something is equal to e, well, e to the power of 1. Since e to the power of 1 is e, if we kind of move in this way, 1, 2. So that's why it's 1 from those exponent and log properties from last day. Okay, now I'm off to the races. Now my x is downstairs and I can solve for it. Being careful that you have the 3x plus 1 in brackets, right? Because then we have 3x plus 1 times 1 is the natural log of 1.5. You don't have to write the 1 even, but I just want to show it since we're just getting started. Okay.
If like anything else was the base, like if it was like adding 3 to the x plus 1.
Yeah.
You could use the log of 3.
Exactly. Yeah, so sometimes I get sneaky and I use a convenient base. So I just force the same base as what the base of the exponent is. That does require you to have the log any base button. Otherwise, you'll have to use the change of base formula. So that would be kind of more work. But yeah, that's the trick. Nice. So now I have 3x plus 1 is the natural log of 1.5. Solving for x now, we're on easy street. 3x is the natural log of 1.5 minus 1. So x must be the natural log of 1.5 minus 1. Oops, brackets in the wrong spot. Minus 1, all divided by 3. Which, although it looks gross, that is just a number. Right? And so this is our exact answer. Most of the time, I'm happy with you leaving it in the exact form, right? That is true, okay? But if we do the natural log of 1.5 minus 1 divided by 3, uh-oh, I did something weird. 1.5 minus 1 divided by 3. I'm getting used to the calculator, my Value Village calculator. What a score. I always check the calculators if I go. Negative 0.198178297 roughly. So just a number. Well, nice. So that number plugged in here should make 9. Right, so you can always check your work, especially if you're solving for an x here, right? What could you do? Keep the number on your screen or store it, right? So make sure you keep all your decimal places, and then times 3 plus 1, and then e to the power of that guy, and then times 6 equals 9. Phew, what a relief. Oh, nice. Good. How about another one? What if we have to solve something like 2 to the 1/2 t plus 6 is equal to 10? First thing we have to do is isolate just this little exponent, right? So we need to chip away. So we need to isolate this. So let's start there. 2 times 1/2 to the t plus 6 is equal to 10. To isolate that 1/2 to the t, first thing I need to do is subtract 6 from both sides. right? So I need to have 2 times 1/2 to the t is 10 minus 6, which is 4. Then I need to divide both sides by 2, so I get 1/2 to the t is equal to 2. 4 divided by 2 is 2. Nice. Now we can take the log, right? And so here, this is where you could use the log base 0.5, right? 1/2. Okay? So here I'll make a note. We can take the log of any base, but log base 1/2 will save us some work. If we have a log base anything button. Otherwise, I'll show you what to do if you don't. Right? If you don't, you would take the log base e or log base 10. Right? I would opt for log base e, of course. And so here, let's do this. Let's solve it with the log base 1/2, and then over here use the natural log. And it's down here. That's perfect, actually. So if I have 1/2 to the t is equal to 2, 1/2 to the t is equal to 2, and I want to solve this, then I can use the log base 1/2 of 1/2 to the t is equal to log base 1/2 of 2. Let's focus on the log base 1/2 or 0.5 for now. So then, that means the reason I did it was to bring this t out front. So now I have t times the log of base 1/2 of 1/2. That's going to simplify to 1, right? Because 1/2 to the power of what equals 1/2? 1. Right? And so here, this becomes 1 is equal to the log of, let's do 0.5 of 2. So now I have t times 1 is the log of base 0.5 of 2. So t then must be the log 0.5 of 2. Which is great if you have that log base anything button, which I need to find on here. There it is. Log base 0.5 of 2 is -1. Oops, I should do it like this. If you don't have a log base anything button, use the change of base. Remember what the change of base formula said? It says that the log base 0.5 of 2 is the same as the natural log. I like to use the natural log, right? Or you can use log base 10, a button that you have, right? The natural log of 2 divided by the natural log of 0.5. If you do that, the natural log of 2 divided by the natural log of 0.5, I get -1 again. So it just depends on if you have the button or not. It's no big deal if you don't have the button. It does make it a little bit easier. Or if you don't have the log base anything button, then you don't get to have this choice where I'm going to take the log base 1/2. So then let's just run through it and just use the natural log from the get-go. So then I need to take the natural log of 1/2 to the t, oops, is equal to, whoops, need to do it on both sides. Log of 2, which puts me at t times the log of 1/2, the log of 2. What you'll see is we end up in the same spot as the change of base formula, okay? Because now t is the natural log of 2 divided by the natural log of 1/2, which is exactly where you ended up here, right? So here, which we know, -1. I'd say I'm gonna stick to my guns. I prefer to just always use the same log and not even think about it. But like I said, there are times where I get sneaky and I use a different base, but just because it's easier. But it took the same number of steps because here I added a line. So I would call it the same length, I guess. Although I wrote out some more steps in the first one, I guess. Roughly the same. Nice. So t would be -1 in that case. And you can try it. That's what's nice about solving stuff is now you could try 1/2 to the -1 times 2 plus 6, and it should be 10. Let's do it. 0.5 to the -1. Make sure it's all in the power. Times 2 plus, oops, try to do 3. 6 is 10. Phew. So that's nice. Any questions about that one? Nice. Kind of fun, right? Tuition is currently $1,050. That'd be nice. I'm assuming it's not anymore. Maybe I'll close this door. It's growing at 7% each year. When will the tuition exceed $2,000? Might be helpful to remember what the exponential function looks like. So each year it's growing 7%, and so that's going to be exponential. Okay? It's going to start at 1,050. So it looks something like this. Let's say we start here at 1,050, and then it's going to grow over some time t. So let's replace x with t just to be more explicit. And what we want to know, and then we have tuition on the y-axis, which we could call capital T. Capital T and lowercase t are different, of course. So at some point, the tuition can be 2,000. Which happens at some time point t. So we need to find that time point t. Right? Okay. Let's see here. What do we know? You might remember that in general, if it's growing at 7% each year, then we have the general form of a times 1 plus r to the power of x. Because it's each year. If it was continuous, it would say continuously. Or we could replace our general F with a capital T for tuition. The tuition after time t, okay, is going to be a times 1 plus r to the power of t. Right? Any x's are replaced with t in this case. You don't have to do that part, but it does make it kind of nicer to look at, in my opinion. Okay. So if you want to just jump in and use this first version, that's totally fine. Right? Okay, just as long as you remember that the output is the amount of tuition and the input is the year. Okay. So our tuition function started at 1,050. Remember, the a is the initial value, right? Times 1 plus 0.07 to the power of t. Now I want to find the t that forces the tuition to be $2,000. And because we know how this thing behaves, right, after that point of t, then the tuition is going to be exceeding $2,000. So we just need to find the point where it crosses 2,000, and then after that, it'll just be more than 2,000. It'll never decrease. I know. Okay, so we want to solve for t when t of t is equal to 2,000. All right. What can we do? Well, we can force the t of t. I'll write it down here. 1050 times, and I'll do 1.07 to the power of t. Save us a little bit of work there. And then I'm going to force this to be 2,000. 2,000 is 1050 times 1.07 to the power of t. This we know how to solve, right? I need to isolate the exponential function, 1.07 to the power of t, which means I need to divide both sides by 1,050. So here we go. 2,000 divided by 1,050 is 1.07 to the power of t. Now let's see. 2,000 divided by 1,050 is nothing nice. So I'm just going to keep it there, actually. It does, my calculator does reduce it to 40 over 21, but just for simplicity, I'm just going to keep it as 2,000 over 1,050. Okay. As long as you keep all your decimal places, you'll be fine. So you can use the store function in your calculator if you wanted to. But I'm just going to keep the, oh, what happened? Screen broadcasting. Uh-oh. Probably decided to do an update. How convenient. Why would it do that? Installing. Although what's confusing is the top is claiming it's still in the meeting, but. Okay. Let's see here. Still recording, that's crazy. Who knows what that looks like? This happens every now and then, and I never go back and see what it looks like. It's probably just a black hole for a little bit. Okay, that looks good. I hope. So I'm going to keep the 2000 over 1050, and I'm going to take, now you could take the log base 1.07. I'm just going to use the natural log. And so here, the log of 2000 divided by 1050 is, are we ready to just do the maneuver? The reason we're taking the log is so that we can move the t downstairs. So let's just go ahead and do that right away. T times the natural log of 1.07. So here, I moved it when I took the log. Which you're allowed to do because that's the whole point of taking the log. You don't have to show the step. So now I'm able to shake out the t. What do I need to do? I need to divide both sides by the log of 1.07. So now I'm left with t. I like to do the revolving door so that what I'm solving for is on the left-hand side, but you'll want to be careful because you still want to have this, the natural log of 2000 divided by 1050 in your numerator and the natural log of 1.07 in your denominator, but we can put them on the other side. Like this. That's the exact answer, of course. But that's really hard to communicate to your friends if they actually asked you, hey, when is the tuition going to exceed $2,000? Right? Oh, it's whenever the log of 2000 over 1050 over the log of 107 is. Right? That's hard to communicate. So in that case, we should probably find the approximate answer. So the natural log of 2000 divided by 1050, making sure that when you use your calculator, you keep all this on the inside of the log, right? Now, since I'm just getting used to this calculator, it's an exciting time. It didn't try to trip me up. So some calculators just try to close the bracket right away. So this one didn't do that, so that's nice, but just keep an eye out for it. I get roughly 9 point. Let's see here. Did I do it? Good. 9.523645992-ish years. So that is the time point here, right? What we found with this 9.52 is that after 9.52 years-ish, right, the tuition will exceed $2,000. Nice. Good. Questions? Might have heard a pH at this point. Probably. So in chemistry, pH is a measure of the acidity or the basicity. is it called basicity? Is that how you say it? I don't, it's basicity, right? I know nothing trips you up more than just saying a word many times over. The basicity of a liquid. The pH is related to the concentration of hydrogen ions, which we denote by this kind of square bracket H with a positive superscript, sorry, measured in moles per liter. And we have this equation where the pH is the negative log of the concentration of hydrogen ions. Okay, so of course that's the log function. If a liquid has concentration of 0.0001 moles per liter, determine the pH. Easy enough. The pH, making sure that the units match. There was clearly a typo here that I fixed, but now I'm curious to know what it actually said. Oh well. The units do match, so that's great. So then the pH is the negative log of 0.0001. This is log base 10. So here, this is log base 10, the common log. And when we talked about the common log last day, I actually forgot that pH is base 10, but there you go. So what does that mean? That means that really what we're trying to find is 10 to the power of something equals 0.0001, right? And from your work with scientific notation, right, you can probably do that work, but you also have a log base 10 button on your calculator, so let's just use it. So the pH is the log of 0.0001 would be 4. And maybe I should do negative 4, technically, which is 4. And so here, confirm that 10 to the power of something equals 0.0001 must mean that y is negative 4. That's this number here. I was gonna say 4, and that's why I hesitated. That's not true, it's too small. What? 1, 2, 3, 4. Good. Okay. And let me just, some more room here. Determine the hydrogen ion concentration of a liquid with a pH of 7. So again, we use the same formula. And this is very similar to what you'll be doing in section 4.6, right? We introduce a formula like this for the pH, right? And then answer questions about it. Introduce a formula, right, that applies to the question, and then you use it. The negative log of plus there. Now I'm trying to solve the hydrogen ion concentration, and I want to force the pH to be 7. So 7 is the negative log of the hydrogen ion concentration. Now I want to get at something inside the log, right? Earlier, we were using logs to get at the exponent, but we can move the other direction as well, where we can raise it to an exponent and it'll have the same effect. And I'm going to put this on a new page, just copying it down. Oh, should be a plus. To solve for something inside a log, we use exponential functions. Or I should say an exponential function. I feel like it's actually recapped here. So it's recapped in the notes for section 4.4, but I'm just gonna snag them now because we introduced them in, I want to say 4.3. Can't really remember. So we've been using this property. The log base b of b to the x is equal to x, right? Because this x moves downstairs and then it's x times 1, right? And so by the same kind of mechanism, right, we're going to use this property. If I take b to the power of log base b of x, then they'll cancel and I'm left with x. Yeah? But in this scenario, it's really important that you have the same base. Yeah? And so here, must use the same base. Yeah? This is log base 10. Right? If it doesn't say it's log base 10. So what I'm going to do is I'm going to take both sides and put them as powers of 10. Yeah? And so I'm going to do this. 10 to the power of 7 is equal to 10 to the negative log, and I'll put the base 10 on there, you don't have to, of the hydrogen ion. Oops. Oh, you know what? I flubbed it. Not too bad. What did I forget to do? I shouldn't have had this negative on here, right? So same as we need to isolate the exponential function, I still need to isolate the log. So sorry, I'm going to bump this down just one line. And it'll be 10 to the negative 7 instead. So we need to isolate the log, which means I get, it doesn't matter how you do it, but that negative has to move over to the left-hand side. So you can divide both sides by -1 if you like, or just multiply by -1. It'll have the same effect. Let me just do this. So then I have -7 is the log base 10 of the hydrogen ions. There. Now I can raise it, which I already did, kind of jumped the gun there. 10 to the -7 is just a tiny number, right? And then 10 to the log 10 of the hydrogen ions, well, that looks exactly the same as this here, right? And so by these properties, right, 10 to the log base 10 of x, basically these cancel, right? And so that's why we did it. We had to do it to both sides. So it did alter the -7 to be 10 to the -7, right? But now these guys cancel and you're left with 10 to the -7 is the hydrogen ion concentration. So very small. Or hydrogen ion concentration is point, let's see here, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7.
Wait, sorry, why did the 10 log cancel out?
Oh, because of this property here. So the reason we did the 10 and then to the power of the log base 10 is because if you have a base b to the power of log base b, they'll just cancel and drop out the x. Nice. Good. Awesome. Any other questions? And that's in moles per liter, but to drive your other profs nuts, I don't care about units. I do, but not as much as they do, I think. They really care about units. We can move between a periodic and a continuous growth rate. And so if you have a periodic growth rate, such as the 7% per year that we saw, right? That's called a periodic growth rate. And so that's this function that we've seen, right? F of x is a times 1 plus r to the x. Okay. And then if you have a continuous growth rate, it'll look like this. F of x is a times e to the kx, where k is the continuous growth rate. Now, you can convert between these by saying that 1 plus r must be equal to e to the k. And so let's just have a look between these two, because if we want to force them to be the same, right, to convert between the two, then we can say that a times 1 plus r to the x is the same as f of x, right? Just kind of using the f of x as a go-between, as a times e to the kx. If you want to mirror kind of what's happening, then what you have is you have an a on both sides and you have a power of x on both sides. And so that's why if you say, okay, well then 1 plus r must be the same as e to the k, right? Then you'll be able to solve and move between the two. So we see 1 plus r must be equal to e to the k. And maybe I'll do pink brackets around this one too, because that's how they'll be the same. Let's bring this up here. If a population grows 10% each year, now this is our clue that it's the periodic growth rate. Find the continuous growth rate. And so here, what that means is that r must be 0.1. And we want to find the continuous growth rate, which is k. Notice that we don't have a starting size a, right? And we don't have a value for x either, but what we'll find is that they don't matter. You can just skip straight to this fact that 1 plus r must be e to the k and move between the two, but I just want to show you that they'll cancel out. And so we have a times 1 plus r to the x must be the same as a times e to the k times x. If I tried to isolate either of those exponents, then I'm going to divide both sides by a, which leaves me with just the canceled a. Oh. Then what I can do is now I have 1 plus r to the x is e to the k times x. If I focus on the left-hand side, for example, what would I need to do? Well, I would need to take the xth root. And so I can take the xth root because I don't have an x. So that's my problem. But I have to do it on both sides. When you take the xth root, what's the trick to cancel those exponents? Well, it's to rewrite it as 1 plus r to the power of x times 1 over x. Right? Remembering those exponent laws that we can write the xth root as a power of 1 over x. And then I have e to the kx times 1 over x. Now x over x makes 1, which is why we took the xth root, and x over x is 1. So now I have 1 plus r. I'll show the power of 1 just briefly. Time is equal to e to the k times 1. Or 1 plus r must be equal to e to the k, which is what we established already. So now we want to let r be 0.1. Solve for k. One plus 0.10 is e to the k. So 1.1 is e to the k. You don't have to have the 0 on there, but because it's 10%, I like to do the 0.10. It doesn't matter, but e to the k. Now, since I have an exponential function base e, I'm going to use log base e as my natural choice, pun intended, because it's the natural log. So k must be the natural log of 1.1. Since e to the power of something equals e, well, that something must be 1. So I'll write out the steps, but you don't have to. Therefore, k is the natural log of 1.10. That's the exact answer. I want you to be careful using an approximate answer, unless it makes something nice, which I really doubt. Doesn't. 0.0953101798. One thing that you could use to check it though, this would make roughly 9.5%, right? And so it should be kind of close to 10%, your answer. So if you're finding that your answer is really far off of 10%, then something probably went wrong, right? But the continuous growth rate will be a little bit lower, right? Because it's compounding continuously, right? And so it'll add up a little bit faster, but what we found is not that much faster, right? And so this 9.5 kind of checks out. I'm happy with that. Nice. Any questions about that one?
You really write 9.5 something percent.
I'd be happy here. I'd give you all the marks here. If you want it. Or here, or 9.53% continuously. Awesome. Just keep them on the same page here. Here?
That's supposed to round up 2 decimal, 3 decimal.
Yeah.
Are you going to do that?
On the test? No, I don't. What I'm looking for is, do you understand this maneuver of taking the log of both sides? And then, so usually I'm not really looking for the answer. Obviously, if I see the right answer, and then I can just kind of skim up and make sure it looks good. But if I see that, then it's easy and I can just move on. But if I don't see the right answer, then I just make sure, and there's kind of big mistakes and little mistakes. But what I'm looking for is, do you know how to solve for something in the exponent? Right? Do you know to take the log? Because it's not a calculator course. We use our calculator a ton, but that's not, it's not the important part, if that makes sense. Okay. We ready for the next section? And I shouldn't trust that clock. Or maybe I should. No, I shouldn't, because it's behind. So someone changed it, but it's still behind. Not bad. Not bad. So, log laws, properties of logs. So the inverse properties we've been using already, right? And so how we solve for the exponent, right, in an exponential function, and how we solve for something inside the log. You have a log function, right? And we leverage the exponential property quite a bit, right? So if you have the log base b of a to the r, so notice it can be any base, right? Then this r moves downstairs, r times the log base b of a, so that's the one that we've been using a ton. And we also introduce the change of base formula, right? But if you just know what your calculator has, then you won't need the change of base formula, right? Just use a log that you have on your calculator. Now, the new log laws for today are these. The sum of logs property says that assuming we have the same base, right, that's going to be important. Then if I take the log of a plus the log of c, then I can rewrite that as a single log of a times c. So that's kind of neat, right? So if I'm adding two logs, I can combine them by multiplying inside the log. Now, I want to add some space for myself here. Hey. The difference of logs property is similar, and we actually don't need it. I'll show you why. Yeah. But again, we have the same log base b. And if we take the log of a minus the log of c, then that becomes the log of a over c. Yeah. We don't need this property stated. if we recall other laws or other properties. I want to show you why. Subtraction is just a special case of addition, right? I'm adding a negative. Okay? So the log base b of a plus the log base b of c to the -1, right? What did I do? I took this subtraction, which is technically, and maybe I should rewrite it before I jump in here, plus -1 times the log base b of c here. Oh. But that's the same as the log base b of a plus the log base b of c to the -1, right? Kind of reverse maneuvering this move downstairs. Do that. Huh? But then, now I have the sum of logs, the sum of two logs, which means that I'm allowed to rewrite this as the log, as long as that they have the same base, right? The log base b of a times c to the -1. C to the -1 is just divided by c, and so you get the log of b, log base b of a over c. So you don't really need that. The difference of log property, it might be nice, right? Because you don't want to be doing that every single time, right? You can remember why it is, but it's pretty easy to derive why that's the case. Huh? Nice. Okay, so how we use these properties is sometimes we use it to expand into multiple simpler logs, right? Or sometimes we use it to contract, right? And just kind of simplify things a little bit. So we'll practice moving both ways. Rewrite the following as a combination of single log functions, and I want to clarify that I want no exponents inside the logs. So we want to rewrite this and just kind of expand it out. So expand. Okay. First thing I'm going to do, right, is use the difference of logs because I have this fraction here, right? And then I can pick apart those logs. And so from the fraction, I'll start with the log. Log is just log base 10 of 5x to the 2 over y to the 4 is the log of 5x squared minus the log of y to the 4. Right. Now, what do I have? Well, I have multiplication still inside this log, as well as a power and a power here. And so, and I want no exponents inside the logs. And so first thing I'm going to do is I'm going to tackle this 5 times x squared and rewrite it as to the log of 5 plus the log of x squared, leaving the other one alone, log of y to the 4th. Log of 5 is simplified, right? Now I'm going to tackle these powers. And so now I have the log of 5 simplified plus 2 times the log of x minus 4 times the log of y. And that's the expanded version of that whole thing. Nice. This up. What if we want to rewrite this as a single log? They both have the same log base. And so here, make sure they have the same base. Otherwise, we can't do anything. They do, log base 10. So if they do, then that's great. Then I can smush them up or simplify. Some people call it simplifying. 2 times the log of x, I'm just going to write it out here, plus 3 times the log of y. I reverse maneuver. Oops, this one looks weird. My exponent first. So I get the log of x squared. That's equivalent to 2 log x. Plus the log of y to the 3. Now I'm adding logs of the same base, which means that I can multiply them inside the log, which means I get log of x squared y to the 3. Nice. Log base 10.
Can you take those 2 out and 2 and 3?
These ones? Do you mean these ones?
Log square and how you can move those 2?
Not technically, no, because you'd have to move back and you'd have to split them up and then do it. Because, yeah, I can't explain why actually. But I think, so how I'm understanding your question is, could we do this? We can't, but I can't explain why. I'll have to look into it, yeah. Yeah, so same explanation. You'd have to split them up first, and then you can move them. But they don't do that. Good. Oh. Oh, let's just give it its own page here. What if we have to solve something like this? Solve the log of x plus 5 minus the log of x is equal to 2. Solving means solve for x. And maybe I'll add a page here instead. Nope. First thing you're going to do is say, okay, well, that's going to be really hard to get at. Okay. The easiest thing to do is to combine these into the same log, right? Because how do we get at something inside a log base 10? We would raise 10 to the power of this thing, right? But if I have 10 to the power of the log of x plus 5 minus the log of x, I'm still kind of stuck. Okay? And so your first step here is to rewrite as a single log. Oh, that's fine. The difference of two logs of the same base, I can rewrite as the log of x plus 5 divided by x is equal to 2. Okay. Summer. Now what? Now I have the log base 10 of this thing, right? And so if I want to get at the x's inside that log, then I take 10 to the power of both sides. Right? And so here, I'm going to have 10 to the power of log base 10 of x plus 5 over x is equal to 10 to the power of 2. You have to remember to do it to both sides. We did the base of 10 for our exponent because then, and let's see if I can find a different color, then I can cancel those and the x plus 5 over x drop out. Yeah.
Confirming, if it was like a natural log, you would put it
Yeah. Yeah, so to get at anything inside inside a log, you have to use the same base. Otherwise, it's just you're just making more work. Whereas if you're solving for something in the exponent, kind of you can choose your own. But has to be the same. But now, by these exponent laws and the log properties, I have x plus 5 over x must be, whoops, 10 to the 2. Almost didn't see it. There's a little bit of work here. Right? I have to solve for x. I think the easiest way to do it is, well, first 10 to the 2 is just 100, and I'm going to multiply this x over here. Yeah.
So when you cancel out the 10 log 10,
Mm-hmm.
the x plus 5 divided by x drops down in the power.
Yeah. 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 And so that's the one that you really want to kind of commit to heart is this property here. Because if you're trying to get at an x inside a log, only way to do that is to take b to the power of that log. And then it drops down. And whatever's inside the log just drops out. And then it's gone. It's not gone, but sort of. So now I have x plus 5 is equal to 100 times x. Because I want to collect like terms, right? I want to collect all my x's on one side and all my non-x's on the other side. And so what I did here, because I can't just cancel these x's because I'm left with 5 over x, right? So you want to be careful when we're adding in the numerator. So that's why I move this x over here. Looks like this. So now you want to collect like terms. So I get 5 must be 100x minus x, putting me at 99x, because it's technically minus 1x, right? And so 5 must be 99x. Now I can solve for that x, and I can't help it. I like to have my x on the left, but as long as you do the same move, 5 divided by 99, I suspect it's nothing nice. No, it's not. But x is roughly 0.0505 repeating. That's fine, yeah. Yeah. Yeah, I'm happy with either one of these answers. You could even do the 0.05 repeating. It's fine. For some reason, I was raised, mathematically speaking, that you do the first few and then show that it's repeating, but I don't think there's any foundation for that. But now I'm stuck. Nice. Good. So, another one. Any questions though? I'll do this one on its own page. What if we have to solve for x in log x plus the log of x plus 3 equals 1? Same deal. Yeah. The easiest way to do it is to rewrite as a single log because we can. I'm adding two logs, the same base, 10. Yeah. Rewrite as a single log, which is why we had to learn those properties. Yeah. And so here, log of x plus, it bothered me that I didn't do it earlier, is equal to 1. Adding two logs means I can rewrite them as multiplying inside the log. So that means I have the log of x times x plus 3, making sure you treat the x plus 3 as one thing. Yeah. Uh-oh, what does this look like? X squared plus 3x inside. So I have the log of x squared plus 3x is equal to 1. Now this is log base 10. I've isolated my log, I've simplified it, so now there's nothing left to do but to take 10 to the power of both sides. Right? So now I have 10 on both sides to the power of the log of x squared plus 3x is equal to 10 to the power of 1. These guys cancel. And I'm left with x squared plus 3x is equal to 10. Which is a quadratic. I know, wild, right? And so we recognize that this is a quadratic. And bump this down here. We want to solve for x, where x squared plus 3x is equal to 10 now. That's the same because we kept the equal sign and we just manipulated it until we got this quadratic that we know how to solve for, right? And so what can we do? If we have to solve for x in a quadratic, right? First thing I want to do is maybe move this 10 over to the left-hand side and set it equal to 0, right? Because that I definitely know how to solve for. So I have x squared plus 3x minus 10 is equal to 0. So this we can solve with the quadratic function, which I have to play around with your calculator, but your calculator does do it for you if you want to. Okay, on the test, if you use the calculator function, which you're allowed to do, I encourage you to do, just write using my calculator, x equals this and this, right? Because you should get two values of x. I'll do it the old-fashioned way. X must be And the important part is that you have it equal to 0. That's when you can use the quadratic function. Negative b plus minus the square root of b squared minus 4ac divided by 2a. I get negative 3 plus minus the root of 3 squared minus 4 times 1 times negative 10 divided by 2 times 1. 9 plus 40, the root of 49, still 7, so that's great. Negative 3 plus minus 7 divided by 2, skipping some work because we've already done a lot of work with the quadratic. So then I get negative 3 minus 7 divided by 2, negative 10 divided by 2, and negative 3 plus 7, 4 divided by 2. So I get negative 5, 2. Now here's the kicker that I haven't been paying attention to earlier, but especially when we get to answers, and maybe I'll scroll back up and check what do I need to check? The domain of a log, right? And so remember, the domain of a log is that x has to be greater than 0. Right? We introduced that last day, kind of parking lot it. But so what we need to do is go back up here. We have the log of x, which means my first restriction is that x has to be greater than 0. Okay. And then I have the log of x plus 3, which means x plus 3 must be greater than 0. Right? And we need the overlap. Okay. So in the log of x plus the log of x plus 3 equals 1, we need x greater than 0 and x plus 3 greater than 0, which means x has to be greater than negative 3. The overlap, and maybe I'll just add a page here. So the domain of the overlap of x greater than 0 and x greater than negative 3 is just x must be greater than 0. Which means x equal to negative 5 is not an option, right? And so therefore x equals 2 is the only option. Therefore, x equals 5 is not in the domain. And x equals 2 is the only solution. Nice. Now we did do some where we only found one solution. Usually I'm prompted when we have 2 solutions to choose from, right? And so admittedly, I forgot. But here I found earlier, we found an x of 0.05, very small, but still positive. And here I need x plus 5, so 0.05 plus 5 to be greater than 0, that's true. And I need x to be greater than 0, so it's okay, right? Maybe I'll add a note. X equal to 0.05 repeating is in the domain adding that in after, so not a good look. But something to keep an eye out for. Oh, and then here we were just rewriting. Nice. So it was just the one where I missed it. Okay. Nice. Any questions? Okay. A word problem. A mini word problem. Town A's population is currently 1,000, growing at a continuous rate of 6% each year. Yeah? Town B's population is currently 5,000, but is dropping at an annual rate of 5% each year. Now, this annual rate tells us which formula we can use, right? And the continuous rate will be different. When will the two towns' populations be equal? Now, we can use what we know about exponential functions to sketch this out. We have the population at some time t in years, and I have t. And we have town A is starting at 1,000. Let's do this in orange. So starting at 1,000, it's growing, right? So this is town A. Whereas town B's population is going to look something like this. It starts at 5,000. Let's put that up here just to keep it on the same graph. Just want to visualize this thing, right? But it's dropping, so that means it's going to look like decay. Town B. When will the two towns' populations be equal? Well, they'll be equal at the intersection. We've found intersections of lines, right? Remember how we found the intersection of two lines? We set them equal to each other, and then we solved for the values that made them the same. And we're going to use the same method, even though we've got these exponential functions. We'll develop what those functions are, and then we force them to be equal to each other, just like we did with that tuition problem where we forced the tuition to be 2,000, right? And so similar, or it's the same idea here, right? I want to find at what t does that happen, right? When will they be equal? Which means we first need to develop functions for each of these population sizes. So if we work on town A had a continuous growth rate. So in general, a continuous growth rate has the form f of x is a times e to the k times x. Or in terms of a population at time t, we have a e to the k times t. A for town A is 1,000 times e to the, and we're told the continuous rate of 6%, which is makes k 0.06. Oops. Times t. Is town B was starting at 5,000 and it's dropping at an annual rate of 5% each year. And so the general form of an annual rate drop would be f of x is a times 1 plus r to the x. Right? So notice how we have to pick the correct starting form. Right? Or in terms of a population size, P of t is a times 1 plus r to the t. We're starting at 5,000 and we have a decay rate, right? So it's dropping at 5% each year, which means that we have a negative 0.05 rate. Right? And so I'll make a note here that R is negative 0.05. Which means that P of t must be 5,000 times 1 plus negative 0.05, which you can simplify right away if you want, to the power of t. Putting me at a simplified function of 5,000 times 0.95 to the power of t. And that t is only on the 0.95. Okay, so now I've got functions representing each of these two. And so now finding the intersection means to force this P of t be equal to this P of t. Right? And so kind of visually, what that looks like is that that happens at P of t equal to this P of t. So let's do that. And it doesn't matter what that number is. Usually we find it just for kind of completeness later on, but because we're forcing them to be equal to each other, they kind of go away in a way. So the intersection is when I have P of t equal to this P of t. Replacing those with their functions, I get 1,000 e to the 0.06 t is equal to 5,000 times 0.95 t. Ah. Did I do something strange? No. I'll just go for it and see what happens. I'll focus on the e to the 0.06 t, right, and isolate this as an exponential function. It's going to be hard to use the same colors. I'm going to do this. 5,000 divided by 1,000. 5 times 0.95 to the t. Now I'm going to take the log of both sides and see what happens. I feel like I did something weird. We'll see it, or we'll see. Log of 0.06 t is the log of 5 times 0.95 to the t. I'll bring that inside the brackets to emphasize. Okay, never mind, I got it. if I use the natural log because I do have e to the power of 0.06t, but also it's my go-to, which means that I can bring that 0.06t down front times the log of e, which is going to cancel, well, make 1. And then I'm left with this kind of a hot mess here. But by the log laws, I can expand that, right? The log of 5 plus the log of 0.95 to the t. So let's do that. The natural log of 5 is just a number plus the natural log of 0.95 to the t. There it is. I have 0.06 to the t is the natural log of 5 plus t times the natural log of 0.95. I want to collect like terms, which means I'm going to move all my t's over to one side and all my non-t's to the other side. I'm going to do that by subtracting t times the log of 0.95 from the left-hand side. 0.06t minus t times the log of 0.95 is the log of 5. Now I can extract that common multiple of t. So here, collect like terms. And now t times 0.06 minus the natural log of 0.95, which is just a number, is the log of 5. And then the common multiple. Now I can solve for t by dividing both sides by 0.06 minus the log of 0.95. So I get the natural log of 5 divided by 0.06 minus the log of 0.95. That is the exact answer, of course. That's hard to communicate though. So let's approximate using our calculator, making sure you keep the 0.06 minus the log of 0.95 all in the denominator. Log of 5 divided by bracket 0.06 minus the log of 0.95. I get roughly, 14.4612296 years from now. Nice. We could do a follow-up. What will the population size be when they are the same? I'm going to keep all my decimal places. I can store it in my calculator, right? Because I want them to be the same. But if I go back and I nab my initial functions, they should be the same. Let's store the exact value in your calculator.
Can't get. I get 26.7.
Maybe I did something weird. Yeah, so you want to make sure this. Yeah. So you want to make sure that when you take the natural log of 5 and then use brackets around,
Yeah, so we double bracket.
yeah, because otherwise it might jump out. It might take the log of 5 divided by 0.06 and then minus the log of 0.95. I think I'll rerun it just in case, but
No,
nice. Yeah, so just be careful with that. That'll get ya. Okay, phew. Hey, now I lost it. Oh well. I use this previous answer button quite a bit, in case you haven't explored it, right? So I just pull in the previous answer, right? Especially if you don't want to work on storing stuff, but I'll store it in A just in case. So now, I stored it in A, so I'm just gonna write that there. So what I can do is I can have 1,000 e to the 0.06 times what's stored in A should be equal to 5,000 times 0.95 to the value stored in A. Okay, so store A times 0.06, and then I want e to the power of that guy, and then times 1,000. I get a population size on this side of 2381.364855. Is that the same as 0.95 to the power of, recall A, times 5,000? Hey, I lost it. 0.95. You really have to press hard on these buttons, I find. I'm not used to that. I'm sloppy. 2381.364855. So they are the same, of course. If you would use a rounded value for t, that's fine, but you'd have to kind of be flexible on them being the same, roughly the same. Close enough. Nice. Good. How about a mini version? I know. But then your video for next week can be shorter. Just graphs of logarithmic functions. I want to focus on the domain of logs, just like we saw, right? So if we find, especially if we find multiple answers, right, multiple solutions, I should say, then you want to check that those answers are in the domain of the log. And so some graphical features of the log, well, in general, it looks like this, right? And of course, you can flip it and you can do all those things, but the basic form of a log looks like this. You have a horizontal intercept at 1, 0. So here, unless it's been moved or manipulated in some way, it'll cross at 1, 0. You're going to have a vertical asymptote here at x equals 0. And the graph is going to be increasing and concave down. Right? It's a cup turned down like this. And most importantly, the domain of the function is x greater than 0, or in interval notation, 0 to infinity, not including 0, right? Because of this asymptote here. So what I'm going to focus on is, if I give you a function like this, find the domain of y equals 5 plus the log of 4 minus 3x. then we need to remember that 4 minus 3x must be greater than 0. If you are happy working with inequalities, that's cool, right? But you want to find a value of x where this thing is always going to be greater than 0. And so we can solve with inequalities, or with the inequality. And inequalities behave the same as equal signs, except when you multiply or divide by a negative, right? Then you have to flip the sign. And so that's why some people don't like inequalities, including myself, because I tend to forget. Now, if I add 3x to both sides, I don't need to change the sign. It's only if I multiply or divide by a negative. So then I divide both sides by 3. 4 over 3 must be greater than x, or x must be less than 4 over 3. If you don't like inequalities, then the first thing you're going to do is solve 4 minus 3x is equal to 0. That you can do, right? 4 is equal to 3x, so x must be equal to 4 over 3. Then use test points on either side. So if you have x equal to 4 over 3, it'll either be less than that or greater than that, and you need it to be greater than 0. Now, 4 over 3 is nothing nice, but x is roughly 1.3. Well, it's 1.3 repeating. So if I want to be to the left of that, I could put it at 1. Or if I want to be to the right of that, I could try x equals 2. Plugging it into 4 minus 3x, right? 4 minus 3x, if x is 1, is 4 minus 3, which is 1, which is greater than 0. Versus 4 minus 3x, which is 4 minus 6, which is negative 2, which is less than 0, which is bad, telling me that x has to be less than 4 over 3, which is the same. I know, I'm out of time. There was just this tiny little one, which I'll sneak into the video where we sketch the graph. And then I've got section 4.6 word problem. I hope you enjoy your break from me, I guess. See you in the video. And I'll see you the following week.
How long is the video?
I haven't made it yet. We'll see how long I blab for.
Please put this here.
No, I limit it to the amount of class time we have.